Okay, today we're going to go through the January 24 exam for the Edexcel International A-Level for Physics, the Unit 6, which is a practical skills in physics. It's the equivalent of Unit 3 in Year 12, which relies on students having done all the core practicals. There are 8 core practicals in Year 12, 8 core practicals in Year 13. So in the Unit 6, which is the final exam, which will probably be for this summer sitting in June, it will be the final physics exam. They can ask you about anything you covered in the 2 years of the course. Okay, so these exams are 1 hour and 20 minutes long, although timing doesn't seem to be such an issue for my students at least, but they do make silly mistakes, so it's important that you practice these while you're revising for your theory exam as well. Okay, so the first question is about oscillations, investigating the oscillation of the stretch spring using the apparatus shown. So if you pull the mass down, it will a small vertical displacement, and that's how you start to oscillate it. The student used the stopwatch to determine the time period t of the oscillation. Describe how the student should determine an accurate value for t. Well, they always want you to put this, so you need to learn this exam technique. Use a timing marker. That means a reference point. For example, you could have something which indicates where the center of the mass was before at the equilibrium point. Okay, so they want it at the center of the oscillation. It's to aid your counting. Okay, so you always put that if they give you a 3-mark question like this. Allow oscillations to settle before timing is the second point they're looking for. In other words, don't try to start the stopwatch as soon as you start oscillating it. Let the oscillation settle down, and then they will keep going for for a while anyway. And then you measure multiple oscillations. If possible, I always recommend 20, yeah, and then divide by the number of oscillations. So in this case, it would be 20. And then, of course, ideally, you should repeat this 3 times and calculate a mean. So as long as you got the main point here, you'll get the 3rd mark. They actually let you talk about repeat measurements of t and calculate a mean as an alternative wording for saying how many oscillations you should use. Okay, then that's the natural frequency of the spring mass system. Everything has a natural frequency. Now the student attaches the spring to a vibration generator. So in other words, it's going to be a forced vibration of a forced frequency. So it won't be oscillating at its natural frequency. It will be oscillating at whatever you set the frequency on the signal generator, which will then feed it to the mechanical oscillator, which is here attached to the spring. So the spring mass system will be oscillating at whatever frequency you set that. Okay? So that's the first part. Then, once you do that, so we're talking about the forced oscillations rather than natural frequency, yeah? The student uses the signal generator to vary the frequency. Well, that's the independent variable, okay? So the student chooses what frequency to look at, so that would be, the independent variable would be on the horizontal axis. And you can notice that on the graph that they've given you, it doesn't need to go to 0, so they've just gone to 0.8 because all their frequencies are between 1.0 hertz and 2.0 hertz. Okay, then, so they've basically got the forced oscillations, so they're telling you that they are forced oscillations. The student then measures the amplitude, yeah, which is a dependent variable, and they put that on the y-axis. This time it does go to 0, yeah, and you can see they've got sensible scales. The scales normally, they want you to go up in round numbers of 2, 0.2, or basically multiples of 2, 5, 10, those kind of numbers. They don't like anything else. Okay, so sensible scales means choosing that. So this one's going up in 5s, this one's going up in 2s or 0.2s. Okay, so the student measured the amplitude of the oscillations for the different values of frequency. So the independent variable affected the dependent variable. The amplitude of A near the resonant frequency. In other words, the resonant frequency is when the amplitude is a maximum. Okay, so the resonant frequency would be here, F0. She plotted the graph of her results. The first question they ask you is determine the value of F0. Okay, so determine the value of F0. So the F0 is there. Actually, I've drawn my ruler slightly wrong, so it should actually be probably this point here. Okay, so I make that 1.52 Hertz. Okay, so I've measured the resonant frequency. Okay, the resonant frequency being when the forced oscillations matches the natural frequency of the spring. That's when the amplitude builds up, and they're going to ask you about that. Okay, so when you're doing this, you should be using a pencil and a ruler. Okay, so that's just an exam technique that I'm reminding my students about. Then once they've got that, they want you to determine the mass, determine the value of the mass. Okay, so when it's vibrating at its natural frequency, which is when resonance occurs, the equation for a spring mass system is period is 2 pi root m over k. K has been given to you. You've got to work out m, and we get t from the graph. So we know t is equal to 1 over f, and we're looking at the fundamental at high amplitude frequency, the f0 on the graph that we just measured. So we measured it as 1.52, so that gives you a period of 0.658 seconds. Once you do that, you want to find m. So remember, we know 4 pi squared. I'm just squaring it out to get rid of the square root, because m is under the square root. So you change the subject of the formula. This is what you'll get if you get rid of the square root sign. K, we know everything apart from m. Basically change the subject of the equation. This will give you the answer, and you just simply put the numbers in, and you'll get to 3 significance figures, 0.329. Well, can you be that accurate? So my recommendation is to keep it to 2 significant figures, because here they're giving you 2 significant figures, but they probably won't penalize you for that. I need to look at that. No, yeah, that's fine. On the previous question, the f0 value that we had, they want this to 3 significant figures definitely, and they will not give it to you if you round it up, because obviously they want to show that you've measured the f0 on the graph accurately matching the peak amplitude. Okay, so 2 or 3 significant figures for here. This is part 2. Yeah, they will give you 2 or 3, so either of these will get you that mark, and the calculation will be the other one. Okay, now they're asking you a question to do with analysis. Explain why your value of f0 may not be accurate. Okay, well, if you look at the graph, the student has only got 6 values between 1 and 2, and really what we're interested in is f0, so really we needed more values around 1.5, yeah, to make sure we got the peak, because of course this will be a curve of best fit, so it's an approximation. Okay, it's a curve of best fit. We're not sure if the peak is going to be there. Okay, now you've got to put that into words. So you really need, so this is what I put. 6 values of f were plotted, only 2 were close to f0. Okay, there are not enough readings taken. So that's one thing, especially around 1.5 Hertz, or you could say between 1.4 and 1.6, where maximum amplitude occurs. Okay, that's O. Okay, so you've got to mention that you haven't got enough readings around f0. Therefore, the line or curve of best fit and the peak value is uncertain, as it's an estimate. The fact that you've drawn a curve of best fit and you've only got 2 values around 1.5, and then none of them are actually at 1.5, it means it's an estimate. Okay, so let's just show you how they have worded it on the mark scheme. So that's part, it's this part, 1B3. Okay, so I'll let you have that on record, so you can slow down the video and take a look at your own answers if you're doing it as a practice paper at home. Okay, that's part 2, and then finally they come back to part C, back to the diagram, and it says the student suggests that the motion sensor, yeah, and the data logger, arranged as shown in the diagram, would improve the experiment. Okay, so everything else is the same, except rather than counting or however they determined before, this time it will be done with the data logger. So Explain how using a motion sensor with a data logger would improve the experiment. Well, data loggers can take many readings per second. Yes, and that's called having a high sampling rate. I think this is the wording they want you to use. So this is the wording they've used in the exam. And it means can take lots of readings per second. Okay, so you'll have a lot of readings, so you'll be more certain of where the peak value will be. So there will be less uncertainty in the measurement of amplitude at each frequency. Okay, so this is the second point. So this is the first marking point, and therefore F0 could be determined more accurately. Yeah, basically you'll have more readings, so the peak will be more certain. Your position of the peak will be more certain. Okay, and if you look back at the mark scheme, it's that I just showed you. That's how they word the mark scheme for the final part. Okay, the next question. So that's the first question, which was 11 marks. The next question is about heat. Okay. So a student investigated the cooling of hot water. Apparatus is shown. So we've got water, glass beaker. So what I always recommend to students is make sure you actually look through every part of the equipment so you notice these things that they're using. For example, the mains powered hot plate. So this is plugged into the mains and is producing heat. So it's heating by conduction through the glass beaker to the water. Okay. The other thing you'll notice is thermometers nicely centered in the water. Okay. The student used the hot plate to heat the water until it boiled. So we're going until it boiled. This is crucial. That means, yeah, we're going to cool it down from boiling point. He moved the glass beaker onto the heat-proof mat, okay, to allow the water to cool. Identify one safety issue and how it will be dealt with. So there's two parts to it: identifying the safety issue and how it can be dealt with. Okay, so the hot plate is one of the examples. Or the glass beaker. The hot plate or the glass beaker will be hot and can cause burns. Alternative to say will be hot if touched, obviously. Yeah, so be clear. Make sure that the hot plate, glass beaker will be hot if touched. Yes, can cause burns. So the clearer you are, the less likely you are to miss the point on the mark scheme. Or you could mention hot water could spill on someone. That's another form of burning. So one of the safety issues is burning because of heat. So the solution, how it will be dealt with is this arrow I've drawn here. The hot plate, turn it off when the water is boiled. So it reduces the risk. Okay, that will reduce the risk of it being off most of the time, just by turning it off. So that's how you're dealing with it. The beaker, you could use tongs or insulated gloves. I remember when I was a student, we would actually get some paper to hold the beaker from the neck of the beaker. Yeah, so we'd actually wrap some paper, fold up some paper, and that would be instead of using insulated gloves. Okay. Now, I'm going to show you the mark scheme for alternative ways that they are accepting the answers for 2A. Okay, so it's there for you to look at your own answers and see if you think you deserve them. Okay, but those are some examples that I put on my sheet. Okay, that's question 2A done. Turning over the page. Now when you're listening back to this, obviously while I'm recording it, I slow down for parts. I try to gather my thoughts. So I'm speaking at a speed which is making sure that I don't miss anything. When you're listening back, I recommend listening to the video at 1.5 speed if you can handle it, and then you stop the video when you want to slow down and make some notes. So what I recommend students doing in their exam technique is to do the questions themselves, write it the way they think it is, and then use my videos to see how they could improve it, and then rewrite it in a different color of where they missed the marks. Okay, so the student suggested, part B, that the relationship between the temperature of the water and time, remember it's cooling, is theta equals theta naught initial temperature, which was 100 degrees if you remember, if it can be kept at that temperature, e to the minus bt. The font, the printout isn't that dark. okay, where theta naught is the initial temperature of the water and B is a constant, okay? Devise a method to investigate the validity of this relationship. The devise a method means write a plan, yeah? So believe it or not, I have students whose first language is not English, so devise a method might throw them, okay? Write a plan. So you need to learn, if your English is not your first language, you need to know what every single word in the exam means. Okay, so we want to test the validity of this relationship. That means we've got to get it into the y equals mx plus c form. And this is one of the main themes in the practical exams, is that you can get any equation, so this relationship, theta equals theta naught e to the minus bt, which is a logarithmic relationship, you can be able to take logs and make it into a y equals mx plus c format, okay? And that's what they want you to do. Your method should use a suitable graph. In other words, how will you get this into y equals mx plus c? Okay, so here's the marks that they're looking for. Use a stopwatch to measure time. Yeah, well, I've put, and the thermometer to measure temperature. So they haven't put this in there, which I wonder what happens if a student put this. Okay, that's one mark. Record theta naught and start the stopwatch. So you want the time to start at the same time. So you could add simultaneously. Okay, so as you're recording the initial temperature, you start the stopwatch. Stir the water. Why is that important? Because you want to make sure that the heat of the water is evenly distributed and the thermometer is recording the average temperature. Okay, record theta at regular time intervals. Example, every 10-20 seconds. Just put something to make sure that you are clear in how often you need to take readings. Keep recording theta and time until the temperature is similar to the room temperature. That means the surroundings. Yeah? Another way of putting it. Because obviously once you reach the surroundings, you can't cool it anymore. So you need to go as far as you can, so it's increasing the range of data. You want to have a good range of data. Okay? And then you finally, 5 marks, 6th mark, the graph. Plot a graph of ln theta against time. Okay? So because if you take log graphs, if you take logs of both sides, you will have an equation. So it will be ln theta, if you're taking log graphs of this, will be equal to ln theta naught, the initial temperature, minus, because the power is minus, you take ln, the e basically disappears, and the minus bt comes there. So then your y equals mx plus c, there's your y, thing that you put on the y-axis. Y is on ln theta. And on the x-axis you've put time, so there's your mx, and there's your c. So it's basically going from ln theta naught, so that will be ln theta naught, and it will gradually decrease, and the gradient will be equal to minus b. Okay? So that allows you to analyze the question, and that's the method that they want you to be able to plan. And if you can get that information that you know you got the correct graph, they will assume you know how to take logs. Okay? And they'll test that in a later part of the exam. Okay? So again, I'll show you the mark scheme so you can see that's where it came from. Yeah? And then you can go back and slow down the video when you want to check your own answers. Okay, the next question is question 3. So I'm just gathering my papers together, make sure I don't put them in the wrong order. So here you got 2 magnets. And the student investigated the force between these 2 magnets. Yeah? So you can see the black end of the magnet, so presumably it's measuring repulsion, but we don't know. Using the apparatus shown, the magnets are separated by distance x. Describe an accurate method to measure a single value of x using a 30 centimeter ruler. Okay? So I'm going to show you the mark scheme in this one. You should include any additional apparatus. Well, first mark that you have to get is this: record the position of the top of the lower magnet, the top of the lower magnet, and the bottom of the upper magnet against the ruler, the 30 centimeter ruler, and subtract one from the other to find x. So this is necessary. Okay. Now, what are the other things that you should do to get an accurate measurement? Yeah. To measure a single value of x. Okay. So what is that? What are they looking for? So here are the other 2 points they're looking for. Any two for, that's the first point that we got. Any two from, ensure the ruler is close to the bar magnets. Obviously you want your ruler to be positioned such that you're measuring it and not creating any random errors by it being misread against the ruler. Okay, so you want to put your ruler as close as possible. So that will get you 1 mark. This one, read perpendicular to the scale. How? Or measure the position of the bar magnets using a set square. So if you've got your ruler there, now if there's two of you, one can hold the ruler, the other can set up the set square, yes, at right angles to it. Okay, so set square, for those of you who don't know, is that right angled triangular measuring device, which is often used to make sure you have no parallax errors, that you're not reading it, because parallax errors, yes, you can avoid them by doing this. 1R. It's a random uncertainty that you're creating by not making sure you're measuring perpendicular to the scale. And then another suggestion they will give you the mark for is clamp the 30 centimeter ruler in position, and then you can use the set square to read off the bottom of the top magnet and the top of the second magnet. And I would recommend this technique. So you've clamped it close to the rulers, and you basically use your set square to get the 2 readings and then subtract one from the other. So this is the underlying principle, and I think this, yeah, is important that you do this, but you need 3 of these points to get your 3 marks, and they're giving you 4 ways of doing it. Okay. All right, so that's what the other 2 marks are, C mark scheme. Okay. Then part B. The student predicted the relationship would be F equals kx to the power of p. Okay, so where k and p are constants. Now, explain how a log graph, now this is not natural log, this is log to the base 10. Explain how a graph of log f against log x, that means log f goes here and log x goes there. Explain how this formula, this expression that can be then logged, can be used to determine the value of the power. Well, if you take logs, they want you to do this. If you take logs of both sides, that becomes log of f plus log of k on this side plus p times the log of x. Then you need to make sure you know how to take logs. Okay, if you can't, that's how you take logs. So this is taking logs. Taking logs and taking natural logs are the same, except log is to the base 10 and natural logs are to the base e, which is a constant in mathematics. Then if you put this on the y-axis and you put log x on the x-axis, because I told you to do that, the gradient will then be the power. The gradient will be p. Okay, so m, the gradient, equals p. And that's how you get the 2 marks. Okay. Then part C, they give you some data. So they test you on all the skills. Planning, now taking logs, taking natural logs, taking log to the base 10. The student varied the distance x, which was on the x-axis in the graph, which is therefore the independent variable, and determined the corresponding force between the magnets. Okay. So obviously if you bring the magnets closer together, the force will be greater because the intensity of the field will be stronger. So that's the dependent variable. So dependent variable is here and the independent variable is there. So taking these values, and what we want to take is logs because we need to plot log graphs. Now when you take logs, the units and the quantity both go in brackets. And this is something that you need to make sure you do both in your table and on your graphs. And that's a marking point for how you put the brackets around the x and the millimeters, or the f and the millinewtons. In this case, you need to do it for both. All right, so once you got that, they want you to plot a graph of that we planned. Log f, plot a graph of log f against log x on the grid that they've given you. Okay, you've got to label the axes correctly, and by that I mean what I just explained. Units in brackets exactly as shown, units and the quantity in brackets. Okay, on the axes. So they will check it. They won't check it here, they'll check it on your graph. Okay, so if you look at the graph, that's all I've done. I put the log of f in millinewtons, and at the bottom I put log of x in millimeters. I'm going to show you that the examiners have done the graph for us, so I'll show you their graph. Okay, going back to the question, there's 6 marks for doing it. So they want you to have sensible scales. Now, sensible scales means that you have got it to like a 2 or a 5 or whatever. Okay, so, and then you get 1 for correct plots of the logs. So you've got to calculate logs first, and you get 2 marks for, presumably you get 2 marks for doing the logs, yeah, to 2 decimal places. So the logs, the log values, you should do to 2 decimal places consistently for all values. Okay, so all the values of the logs need to be in there. So here are the values that they've done. So you'll get 1 mark for getting, see, they've got all to 2 decimal places, all to 2 decimal places. You see how they've done the units? Yeah? And then they plotted the graph. Okay? So here's their graph. Their graph is a bit smaller, and the photocopy is quite faint. So I made quite a mistake when I was trying to draw my lines. Yes? So I've done my measurement here, because once you've done that, yeah, to get the graphs, then you got the correct values for the log f values in the table. So you get 1 for the log f values, you'll get 1 for the log x values, all to 2 decimal places. Okay, they would accept it as long as you're consistent 3 decimal places, but you can't plot 3 decimal places. Then they would have given you the axes labeled. So you see the way they've done that. This and this, the bottom, both axes must be labeled as shown correctly. So 1 for labeling, 1 for choosing sensible scales. They're going up in 0.1s. Yeah, so 1 is fine, 0.1 being divided by 10. And here they're gone up in 5s, 0.05s. Okay, so it's 2, 5, 10. Those are the normal values you go up in, 1, 2, 5, or 10. So they got the sensible scales. This person will get 1 for the scales, and if this was a student's work, and that values are missing. So what they'll do is they'll check on the graph the points which are furthest away from the line of best fit, and they'll see if they agree with the 2 points, for example, that are furthest from the line of best fit, that the students put them in the correct place. And if you have, you'll get the mark for correct plotting. If you haven't, they think that you're more than a millimeter out on the graph, then you'll lose the accuracy of the plotting. Okay, and then draw the line of best fit, and they have to agree that you have drawn a line of best fit. Okay, so that's how you get 1 for the line of best fit. So 4 marks on the graph and 2 marks for doing the data for the table. Okay, once you've done that, we'll come back to the graph. Once you've done that, it said determine the gradient of the graph. So show a large triangle with the values on the graph. Okay, so I did all of my calculations using the examiner's graph. I put my values in, so I can show you that my change in x here is from 2.28, that's the values I chose, and 2.03, so I made a mistake on there. So again, because they're very faint lines, you see, in the real exam you'll have a much nicer printout. So the lines are very faint, so I've worked out the delta x, and I've done the same with the delta y. I've used 1.00 because it's a nice value, and it's 0.10. So here we got that. Now really, I should have shown the delta y as being negative because it's a negative gradient. So what I did in my calculation, I went, instead of being 1 minus 0.0, I changed it to 0.10, the final value, minus 1.00, the initial value. And then I divided by delta x because you need it to be a negative value. Okay, so you could then do this calculation in the space provided. Okay? If you do that, a large triangle gets you 1 mark. Showing the values on the graph gets you the second mark. And the value should be 2 or 3 significant figures, they're saying. Okay? Show your calculation though. So do it the way that I've done it, and there's no harm in you doing it on the graph. They won't penalize you. It's easier to do it that way, and you should always have a large triangle. If you use a small triangle, you can lose a mark. Okay, hope that makes sense. That's question 3B done, 3C done. Graph we did with the examiners. It then goes to an analysis of the data. Okay. So the student suggests that the relationship between f and x is an inverse square relationship. That means the power would be a 2. Explain whether the graph supports this suggestion. Inverse square law means that f is proportional to 1 over x squared, or f is proportional to x to the power of minus 2. It's the same thing. Yes? This means the same as f over 1 over x squared. So as long as you know what inverse square law means, you get 1 mark. Then it says, which would require the gradient calculated from the graph to be minus 2.0. Okay? Now, but our gradient is 3.6. So you're saying, well, it's meant to be 2 if that inverse square law is true. So it's not an inverse relationship. The equation would be more k to the power of minus 3.6. So student is incorrect based on the data provided. Okay, and that's how you get the 3 marks for the conclusion. All right, here's, I think, the final question. Yes, question 4. So here a student made measurements of a semicircular, of a circular convex lens as shown. So this is a round lens, and this is what it looks like from the side. It has a thickness T in the middle, a diminishing thickness as you go to the ends. Okay, so the front view and the side view. The student used vernier calipers. Remember, there's vernier calipers and digital calipers. Don't get confused. They're different. To measure the diameter D. Explain one technique she could use to measure D. So D is from there to there. So you would repeat measurements of D, obviously, at different orientations and calculate a mean. Because it may not be perfectly circular. So you need to, for example, measure it here, measure it there, measure it at different angles, and you'll then take the mean diameter to get the first marks. Why do you do that? To reduce random errors. Yeah, so that's what it's looking for. And it's also that it may not be perfectly circular. Okay, so if you just do it once, you might have a different reading if you do it twice. So by repeating, you reduce random errors. So they want you to know what are random errors, and they want you to know what are what's the other word? Systematic errors. Okay, so systematic error would be something like it has a 0 error on it. So here's the mark scheme they're looking for. Yeah, to reduce the effect of random errors. They're giving you a different way of doing it, so that if, for example, you check that there's a 0 error on the calipers. So if the calipers weren't set on 0, you might have a 0 error, in which case you're eliminating systematic errors, whereas the answer we put was to eliminate random errors. So you can tackle it by minimizing random errors, or you can tackle it by linking your idea to whichever type of error it would reduce. But you do need to mention these words specifically. Okay? So that's for A, part 1. And then part 2, the student estimated the thickness in of the lens in the side view. Was approximately 5 millimeters. Okay, so they're telling you it's approximately. Explain the most appropriate instrument the student should use for a single measurement of t. Okay, your answer should include a calculation. Well, I'm assuming it will work. Most appropriate instrument would be a micrometer screw gauge. Why? As it would have the smallest percentage uncertainty. You need to be that specific because its resolution is 0.01 millimeters. So micrometers can measure to 0.01 millimeters. So if you try to do it with a vernier caliper, which is what they measured the bigger diameter with, vernier calipers have a resolution of 0.1 millimeter. However, digital calipers now have resolutions which are the same as a micrometer, which is 0.01. And if you know, the percentage uncertainty is half the resolution divided by the reading. Well, the reading is approximately 5 millimeters. So if we use one of these, it'll be half of this value, which would be 0.005 divided by 5, which is approximately 0.1 millimeters, because it says your answer should include a calculation. And that's what they're looking for, that you can work out the percentage uncertainty if you used an instrument with a resolution of 0.01. For your exam, percentage uncertainty is half the resolution, yes, divided by the reading. Okay, that's the first part. Now, obviously we're looking at a lens, so then they're doing an experiment with a lens. You don't necessarily have to know about lens theory, they just have to understand the experimental technique. The student placed the circular convex lens in a holder, yes, so that's what they did, and they got a screen here. So remember, they got a filament bulb and a mesh, a wire mesh, and this will produce an image on the screen. Okay, and you can adjust the distance from the wire mesh, which is basically the object you're looking at on the screen. The bulb is just there to illuminate the mesh, and then you can alter the distance here, so which will also affect the distance from the lens to the screen. So you've got two distances which can both vary. Okay, so as U goes up, V goes down. Set up the apparatus as shown. There's the experiment, and then here it says what the student did. The student moved the position of the holder until the lens formed a sharp image of the wire mesh. So basically they're trying to get a sharp focus because that will allow them to work out the focal length. She measured the distances U and V with a meter rule. Okay, so put a meter rule. They're not asking us about how to measure with a meter rule, I don't think. The student determined the focal length of the lens using this formula. Okay. Now, this is not a core practical, so this is not something you've tried. They just want to see if you can analyze, if you've given a formula, if you can use your analytical skills mathematically. Okay, show that the uncertainty in F is about 0.2 centimeters. Okay, well, they've given you the values of U and V, and therefore the focal length. Okay, so we know the focal length, and they're telling us that the uncertainty of each measurement is 0.1 centimeters. Okay, now there's a second method that you could use, but I'm using this method. To work out the percentage uncertainty of F, which is on this side of the equation, you need to know the percentage uncertainties of U and V. Okay, and you need to know the percentage uncertainty of U plus V. So it's basically three things that you need to be aware of: U, V, and then on the bottom the denominator is U plus V. So the percentage uncertainty in F, the final answer, is the percentage uncertainty of U plus the percentage uncertainty of V plus the percentage uncertainty of U plus V. Okay? Now we know the real uncertainties, or the estimated uncertainty of taking the reading. Okay? They're given it to us. So if you want to work out the percentage uncertainty of U, you basically take the uncertainty that's quoted, 0.1, divided by 29.6, multiply by 100, that's the percentage uncertainty, which gives you 0.34%. Do the same for V, 0.1 divided by 19.2, multiply 100, gives you a percentage uncertainty of 0.52. And this time for U plus V, you've actually got two readings in there, so each one has a 0.1. So you've got a 0.2 uncertainty when you add the two together, because you're adding two distances, you also add their real uncertainties or their estimated uncertainties. So the two uncertainty is 0.2 because you're also is 0.2 out of a total of these u plus v added together. So percentage wise, it will be the average of those two. Okay, you can see it's halfway-ish between these two values. Okay, so you've got 3 percentages that you worked out. So this is what they want you to be able to do to analyze percentages. Okay, when you add them all up, it comes to 1.27. We don't tend to offer percentage uncertainties to more than one decimal place, so it's approximately 1.3%. So that means we know 11.6 is plus or minus 1.3%, and 1.3% of 11.6 is 0.15. So the total uncertainty is approximately 0.2, which is what they wanted us to find. Show that the uncertainty in F is about 0.2. So there is a second method of doing it where you'd work out the minimum value and the maximum value for each one, but I think that's a more what's the word, convoluted method, shall we say. Okay, and that's 4b part 2. If you want to see how they've done it on the mark scheme, those are the two methods. Can you see all that? So my method is the top method, and there's an alternative method where you can work out the minimum F and the maximum F and then work out the difference. Okay, then that will give you the uncertainty as well. So I'll just make sure you've got the second method. Yes, you do. And the first method, yeah, so I did the either method. Okay. All right, so that's question 4b. And there is a 4c, which finishes off this paper. So 4c, it says the refractive index of the material used to make the lens is determined using this formula. So it's n equals 1 plus d squared over 8tf, where d squared is the diameter of the lens, t is the thickness that we measure, and f is the focal length, which we calculate as so all the values are given here, d, t, and f. All you got to do is put the numbers in, and you'll come up with 1.63. Okay, so you should quote it to 3 significant figures. Okay, because we know them to 3 significant figures in all cases. Okay, so if you put the numbers in, get the answer out, you get your 2 marks. Now it says determine the percentage uncertainty of n. Well, n, there's no uncertainty in the 1. All the uncertainties in the 0.63. So this value here is equal to 0.63, isn't it? So all the uncertainty comes from here. This doesn't, 1 hasn't got an uncertainty in the equation. So you could say, and that's what I tried to write here, the percentage uncertainty of n total is the percentage uncertainty of this, which is 0, plus the percentage uncertainty of that. It's a bit more complicated than the last one. So let's see if we can muddle our way through it and to explain it to you as clearly as possible. Okay. So the percentage uncertainty of the fractional part, so this part, let's say the 1 plus the fraction, yeah, which is the 0.63 part of it. The percentage uncertainty of fraction is 2 times, it's basically the fraction is made up of this equation. So there's our fraction. There's where all our percentage uncertainty comes from. It's 2 times the percentage uncertainty of d, because it's d squared. So each one has its own percentage uncertainty, so it's like having d twice. So it's 2 times percentage uncertainty, plus the percentage uncertainty of t, plus the percentage uncertainty of f. Okay? So that's how you work out the percentage uncertainties. Now this doesn't have a percentage uncertainty, we're only looking at the fraction, and that's what I'm keen to point out to you. Okay? Once you do that, you put the numbers in, you did it like last time, so it's 0.02, yes, the data given here, 0.02 over 5.02 multiplied by 100, double it up, it comes to 0.797, so that's that one. This one comes to 0.01 over 4.28, yes, and that's, you need to make sure you put it in the correct units, yeah, so it's, if for the percentage doesn't matter because it's the same fraction, okay, but over here, I forgot to tell you, make sure you've changed everything to centimeters. Use centimeters throughout. You don't have to use meters because they're all in centimeters. And it's just actually 2 lots of centimeters divided by 2 lots of centimeters. D squared, 2 lots of centimeters. TF, 2 lots of centimeters. Sorry. Both of these centimeters squared divided by centimeters squared. Okay? So it doesn't matter that you're not using SI units. So you see there's quite a lot involved in these practical skills exams. So you do that for the final value is 0.2 divided by 11.6 multiplied by 100. So there's your third one, gives you a total percentage uncertainty for the fraction in this part of 2.8%. Okay? But that's not the total uncertainty of n. Okay? We know n, most of n comes from the 1. This is a smaller part of it. So this is the real uncertainty of the fraction is therefore 2.8% of 0.63. So it gives you a real uncertainty of 0.0176. So it means that we don't know the second decimal place that accurately. So you could say it's 0.63 plus or minus 0.02. So we kind of know it to 2 places. So the percentage uncertainty of n, however, is going to be equal to this uncertainty because all of the uncertainty comes from the fraction. No uncertainty from the whole number. So the total real uncertainty is that divided by the total value n, which was 1.63. Okay? And when you do that, you'll come up with a value which is 1.1%. I'm not sure many students will be able to get that part. It's quite tricky. But that's why it's at the end of the exam. So don't worry about it if you haven't got it. It then tells you the refractive index of crown glass is 1.52. Yes? Well, here we got 1.63. So they want to ask you about, are they similar enough? Deduce whether the lens could be made of crown glass. Well, using the percentage uncertainty calculated above, n minimum would be removing 1.1%. So it would be 98.9% of this, and that will give you a value of 1.61. Yes? So if it is 1.61, it's still way bigger than 1.52. Lens could not be made of crown glass as the minimum value is still way higher than 1.52. So that's the final bit of the calculation. So that's quite a tricky question to finish off with. Yeah? And if you like, I can show you the bits that we just did, which is 4 part C. There's the mark scheme for it. Yeah? And that brings us to the end of the exam. Well, if you found this useful, thank you for watching. Please like it, share it with any of your friends who are doing the same exam as you, and please subscribe because you will know when the next video will be ready. Okay? Thank you again for watching. I'll be doing more of these videos as I do some practice exams with my own students. Bye for now.